Hello everyone, welcome to the second session of a video series on embedded systems. In the previous session, we discussed about what are operating systems and the detailed concept about process. In this session, we shall deal about threads and task. So let's begin. Thread. A thread is the primitive that can execute a code. See, when I say primitive, I mean the smallest execution part or the smallest or the simplest execution part that a user can get. So, a thread is nothing but a set of execution or a set of codes that can be executed. Now, what is the relationship between a thread and a process? A thread is a single sequential flow of control within a process. Or I can say a thread is a process within a process. You have a main process, say main process 1. Under that, if we have sub-process or a smaller lightweight process, those lightweight process is called a thread. So, a thread is nothing but a process within a process. I can show you a schematic of that. See, here we have a main process here, whose sub-processes are these. These sub-process or lighter weight process is called a thread. A process may have a number of threads, multiple threads, each performing a smaller task, which are subtask or sub-process for the main process. So, a thread is a process or sub-process within a process. It has its own program counter, stack pointer, stack, everything. It is a thread has all the components that a process has. That's the program counter, the stack pointer, the stack, the status registers, everything. Right? I will come back to this. Right? Okay. So, a thread is a lightweight process. Without a main process, there cannot be any thread. As you have seen here, without this main process, you cannot have any kind of thread. The thread depends upon this main process. Right? Okay. So, a thread is simply a lightweight process which is in execution, and it comes under a process. A process may have multiple threads. Now, a single thread can have its own set of resources, which are the status registers, the program counter and the stack. As you can see here, right, the thread has the stack and their elements. Now, when a multiprocessing operating system runs more than one processes and each process consists of multiple threads, it is called a multi-threaded process. Okay. Multi-processing operating system, what does that mean? An operating system which is doing more than one process at a time is called a multiprocessing operating system. So, a multiprocessing operating system can run more than one process at a time. When each of this process contains multiple threads, as you have seen in the previous figure, they have multiple threads, right? In such a case, you call the process a multi-threaded process, right? A process which has multi-threads is called a multi-threaded process. Now, here I can consider a thread as a daughter process. Here, as you have seen here, this is the parent and these are their daughters. So a thread can also be called as a daughter process, right? And they basically define the minimum unit of a multi-threaded process that an operating system can schedule into the CPU, and they can also allocate other system resources to these threads, right? Let me make this a bit more clear. Okay, see, consider your mobile phone display. What are the things in this mobile phone display? We have, let me see, we have the time, right? Here we have the time. Let me show you here. Oh, no. We have the time, we have the power, the battery, your range, um, the connection for headset. All those things are displayed in the time, right? And we also have so a mobile phone display is the best example for to tell you about the multiple thread. There is a thread to display this time. To show that time, we have a thread. To show your battery level, there is another thread. To show the signal power, you have another thread. So to show the connectivity, the device is connected to your mobile phone, you have another thread. This thread is nothing but small processes, right? And the whole process of display is divided into smaller processes, which makes me rectify any issues easily, to make better utilization of the memory. And see, I can also make sure my system is working, my execution is faster, right? So threads are lightweight process or daughter process of a main process. When a process has a number of threads, more than one threads, you call it a multi-threaded process. And that's what I was telling you. Your mobile phone display, you have a part to show your time, date and time, that is one thread. You make use another thread to show your battery capacity, that's another thread. And you can use another thread or a smaller process to show the connectivity, the range, right? The range, signal strength of your mobile service provider, right, for your SIM card. So these are different threads which we are using simultaneously, and that's what multiple thread means. Now, what is the advantage of using this multiple thread? As I have said, they make sure you're using your memory in a better way. See, for a single process, for the same process, the multiple thread, they share the same address space. So in fact, this because of this, you can reduce the issues which may arise due to inter-thread communication. Because see, your date and time, if they need any data pertaining to your battery for later reference or your connectivity, so these threads can in fact pretty easily communicate between them, right? That's how memory utilization becomes a advantage. Another advantage is execution of the process. Your process execution speeds up. See, since we are splitting a single process, the mobile phone display, this is my process. Since I am splitting this process into several different threads, see, all these threads can be executed simultaneously. When one thread is executing, perhaps the other thread is waiting, or other thread has just completed its execution. So in fact, I can use all these threads in simultaneously. As a result, my process execution speeds up. and because of this your CPU utilization is also efficient, right? So using multiple threads help you get better memory utilization, speeds up your execution process and makes your CPU utilization much more efficient. Okay. Now what are the different types of threads that are available? I hope what are threads that is clear to you. It's nothing but a lightweight process. A process within a process is called a thread. And the concept of multiple threads, their advantages, that's what we have discussed so far. Now let's see what are the different types of threads. We have the user level thread, kernel level thread, many to one thread, one-to-one thread, and many to many threads. So let's see what are these. The user level thread. See, the user level thread, they don't get any support from the kernel's operating system because they exist only when a process is running, only when the user is accessing the process. Hence the name user level thread. So the user level thread doesn't depend upon the operating system. They exist only when your process is being executed. See, even if a process has a number of user level thread, the operating system can see it only as a single thread, and they cannot switch between these threads. See, we have seen earlier that when you have multiple threads, since they share the same memory space, it's easy to communicate between these threads, right? But when it comes to user level thread, even if you have 10 user level threads, the operating system can see these threads only as a single thread, right? And because of which you cannot switch the execution between user threads. I hope I have made myself clear. Okay? So that's about user level threads. They do not get any kind of support from the kernel's operating system. So if you have a user level thread, the another kind of thread will be, of course, the kernel level thread. Here, these are with respect to the kernel, these are the only threads. The kernel level threads, they are the basic units of execution, and here the OS, the operating system, can treat each thread as separate thread, not in the case of user level thread. If you have 10 kernel level thread, the operating system sees 10 kernel threads, no difference. That was not the case of user level thread, right? So, since the operating system can treat each thread as separate, it is also easy to switch the execution from one thread to another. Okay, right. The third kind of thread is many to one model. See, this is what we said in the case of user level thread. Here we can map the multiple user level threads into a single kernel thread. You are mapping your 10 user level threads into a single kernel thread, hence the name many to one model. So as we have said, here the kernel treats all the user level threads as a single kernel thread, because of which there is no switching between threads, right? The other type is the one-to-one model of thread. Here, each user level thread is bonded or is connected to a single kernel level thread. You are bonding one user level thread to a kernel level thread. This will lead to one-to-one models. See, Linux threads are examples for this one-to-one model. Another kind of thread is the many to many model. Only in this kind of modeling we can model or we can connect multiple user level threads to multiple kernel level threads. Only in this kind of modeling. So basically, if it is in the user level thread, all the user level threads are mapped into or considered as only one thread by the kernel. But when it comes to many model, in that kind of modeling, the kernel can map each user level thread into separate kernel threads. These are the different kinds of threads available. So, in threads, we learned what is a thread, what are the elements of a thread, what do you mean by multiple thread or multi-threading, what are the different types of threads. I hope this is clear so far. If so, let's see what is the difference between a thread and a process. This is very important. A thread is a single unit of execution and it's a part of a process. See, we have said that thread has its own stack pointer, program counter. But a thread does not have its own data memory and heap memory. This data memory and heap memory is always shared with the process. And if a process has 10 threads, all the 10 threads will share the same data memory and heap memory. So there can be multiple threads in a process. The first thread or the main thread will call the main function and they will occupy the memory for the process. See, this is very important. A thread cannot live independently. It lives within the process. Without a process, there is no thread. And threads are very inexpensive to create because once you have a process, you don't have to spend much memory to create thread because thread doesn't have its own data memory, right? So threads are very inexpensive. Expensive we relate here with in terms of our memory, okay? That's why we are saying threads are very inexpensive. And here again context switching is inexpensive and is pretty fast because you can switch between threads very easily because they lie in the same memory region. So you can switch easily between the context. And finally, we can see that if a thread expires or if a thread has completed its process and it's done, then the process gets to take hold of the stack. Since the thread has its own stack pointer, program counter, once a thread expires, the main process, when I say process, it's a main process. The main process get hold of the stack. These are the main points with regard to threads. Now let's see the same for process. The process has its own code memory, data memory and stack memory, which the thread doesn't have. Now, as we have seen, a process is a program in execution and it has number of threads. The process doesn't depend on threads, but the threads depend upon process. Now, each process will have at least one thread, and the threads within the process share their code data and heap memory. If a process dies, we said that if a thread dies, the process gets hold of its stack. Now, if a process dies, all its resources, its memories, its stack pointer, program counters, all the registers are reclaimed by the operating system. And all the resources allocated to the thread also dies. So if a thread dies, the process take hold of its resources. Now if a process dies, automatically the thread dies, no doubt. And all the resources of this process is reclaimed by the operating system. Okay, I hope that hierarchy is clear. Now, to create a process, it's very expensive because it involves a number of memories, number of operating system overhead. So, process is an expensive thing compared to threads. Threads are very inexpensive. And again, in the case of process, their context switching is very expensive due to the same reason. Okay, so this is the difference. These are the difference between thread and process. This is a very important session, right? Hope I have made clear between process and thread. Okay, fine. Coming to our next topic, task. See, I would like to call process, thread and task three sides of a pyramid. In fact, all these three are very closely related. We saw that you have a process which is nothing but a programming execution. A smaller process or a sub-process within the process was thread. So, the process and thread has very strong relations. Now, what is a task? What is a task? Task for us, task is nothing but a set of duties, right? That was the same as process also, right? What is process? Process is also a set of duties. So, task is nothing but process in a real-time operating system. In real-time operating system, instead of process, you use the term task. So, task is nothing but process in real-time operating system. See various RTOS, RTOS means real-time operating system. OS is operating system, RT for real-time. So, RTOS means real-time operating system. So, we have a number of RTOS like VxWorks, MuCOS2. These are different RTOS. So, they commonly use the term task. Instead of process, they are familiar with the term task. Now, similar to a process, the task also contains executable program codes. These codes are controlled by your operating system. And just like your process, the task also has different states. They may be in running, blocked or finished, right? That's again similar to a process. Now, you can call task as an independent process because no task can call another task. You have task 1, 2, 3. I cannot use my task 1 to call task 2 or task 3. So, all the tasks are independent. You cannot use one task or one job. When I say task, it's some set of codes, right? I cannot use one task to call another task. But I can make a task to send signals or messages that can let another task run. I cannot use a task to directly call another task, but I can signal or give some messages so that another task will identify that message and run. Now, see, basically the operating system can only block a running task. They can block a running task and let another task gain access of the CPU. Not simultaneously. The operating system must block a running task and give the execution to another task. So, see, let's see what is a task. See, we have different tasks which is independent, unlike the other cases, and each task we define TCB, task control block. Just like we had the process control block, here we have the task control block. So just like process, tasks are also embedded program computational unit that runs on a CPU under the state control using task control block and are processed concurrently. I hope the idea behind what is a task is clear. Task is nothing but a process in a real-time operating system. Just like the process has its memory and components, the task also has their necessary resources. And just like the process, they also have different states: running, blocked, finished, created, idle, different states of execution. And you cannot use a task to call another task. You can only signal or message another task, right? Hope these things are clear. Now let's discuss the different states of a task, just like that of a process. So here we have basically 4 states: the idle state, the ready state, running and blocked. See here, in fact you can define each state. The idle state or created state. Here the task has been created and the memory has been allotted to the structure. However, this task is not ready because their entry has not been scheduled by the kernel. So in the ideal state, your task has been created and memory has been allotted. I hope you can spot the difference between the task and a process here. Right. Now, when does this task in ideal state move to the ready state? Once this created task is scheduled by the kernel. I have given a time, okay, your task you will run next. So when the schedule is ready, the task enters your ready state. But they have not yet started execution, right? They know their schedule and they are ready to be executed. Once they start executing, that is the running state. Okay. Now, when does it enter a block state? So, whenever the execution of the task is suspended, they enter the blocked state or waiting state. Once from the blocked state, they get a signal or a message to continue running, they will start running. And then, once they completed their execution, they will get deleted or finished. Okay, so these are the different states present in a task. These are almost similar except what happens here, right? Here task is created and memory has been allotted. They are just waiting for their schedule because in ideal state they don't have any schedule. Once the created task has a schedule, they are in the ready state. Once the ready task is being executed, they are running. When suspended, they are blocked. And once they have completed their operation, they come out of it or the task is finished or deleted. Right. Now let's see, just as in the case of a process, what are the elements of the task control block? In fact, this is almost similar to your process. I just have to read it out. The task ID, just like we had the process ID. Task priority, again similar to the process priority. And you have the address to the next task TCB. Now you have a set of memories. Set of memories for the program address, for the data address block, heap. If, I hope you remember what is heap. Again, stack address and address for CPU register save areas. And yeah. So these are the things that a TCB, the task control block, has, and it can be seen over here. The task ID, the set of memories, I have to say, the priorities, the context initialization. See, in the context initialization, they have a pointer to the start address or starting function, a pointer to the context data structure, pointer to new task, and pointer to the previous stack position. So these are the elements in a task control block, right? So we have discussed what are threads, and then we began with task. We saw how similar task and process were. We also saw the elements in a task, their states and their TCB. Next, let's discuss what is multiprocessing and multitasking. I have already said what is multiprocessing, right? When your operating system can execute multiple processes simultaneously, that's called multiprocessing. Now, how is multiprocessing different from multitasking? See, multitasking is nothing but it's the ability of your operating system to hold multiple processes in memory. The operating system will hold multiple processes in memory, and then they will switch the processor from executing one process to another and another. This is called multitasking. See, suppose, you students have 3 jobs. That is, you are watching my online class, then you have to read the notes, you have to attend your assignment. These are the 3 tasks, right? Listening to video lecture, task number 1. Reading the notes, task number 2. And third task, writing the assignment. Now, how is this multiprocessing and multitasking? Let me see that. Now, one student is listening to the video class, reading the notes simultaneously, and writing the assignment, which means he is doing the task 1, 2 and 3 simultaneously. This is called multiprocessing. At the same time you are listening to this video lecture, you are reading your notes from your, say, laptop, and you are writing. You are doing 3 processes at the same time. This is called multiprocessing. Now, what is multitasking? I have all the resources for the video lecture. I have made my mobile phone ready with the video lecture. I have set it aside. I have opened my PC and I have placed my notes ready to be read. And in the next section, I have placed a paper to write my assignment. So now what I do is, for 10 minutes, I have listened to this video. Okay, so I am doing task 1 right now. After 10 minutes, I will go read the notes, which is task number 2. And after again 10 minutes, I will stop reading the notes and I will go to write my assignment, task number 3. So what I have done is, I have made all these 3 tasks available. For some time, I am switching myself to task 1. After some time, I switch myself from task 1 to task 2. And again, I am switching the person from task 2 to task 3. Here, this kind of execution is multitasking. You are switching the person from one task to another. But if a person is watching this, they feel that you are doing multiple tasks at the same time. So it creates an illusion that multiple task is being executed in parallel. Okay. So multiprocessing, doing all the three process at the same time. Listening to videos, reading notes, writing assignment, all at the same time. Multiprocessing. Multitasking means I have allocated resources for my different tasks in memory. All the materials to do the three tasks is ready. Now I switch my processor or the CPU from task 1 to task 2, then to task 3. Creating an illusion, creating a feeling that all the tasks are being done parallelly. Right? I hope this difference is clear. Okay. Now let's see what happens when you have to switch from one task to another. See, when you switch a CPU from one process to another, you call it context switching. Now, when you switch your CPU from task 1 to task 2, all the details, the registers, memory, system resource for task 1 have to be saved so that later the CPU can come and start from where it stopped once. This is called context saving. So the act of saving the current context, which contains the context details, all its memory details for the currently running process at the time of CPU switching, is called context switching. Okay. And once the CPU is ready to come back and retake the task, you will have to get back the saved context, and that is called context retrieval. Switching the CPU from one task to another, called context switching. When you switch from current task to another, all the details, all the memory, resources, everything about the current task must be saved. That is called context saving. And once you want to come back to your old task, you have to retrieve, you have to get back the saved context, and that is called context retrieval. So that's about multitasking. So here you can see how multitasking is being done of when different processes are in their different states, their idle state, running state. How multitasking and switching of CPU is being done. So in this session we discussed about threads and task. I hope the difference between process, thread and task is clear. Just go through your notes once again. In the next session, we shall see different scheduling algorithms of task and different types of multitasking. Thank you.